Hello, this is Glenn McCallum, and I'm going to talk about Chapter 1 of scaling networks. Yeah. So Chapter 1 covers wide LAN designs and also campus network device selection. So wide LAN designs. And so basically, a company with a small network with one site and a connection to the internet might grow into an enterprise with central location and numerous remote sites across the globe. All enterprises networks must support the exchange of various types of network traffic, support critical apps, support converged network traffic, support diverse business needs, and provide centralized administrative control. The LAN is the networking infrastructure that provides access to network resources for end users over a single floor or a building. So, hence the name local. So, how do we design this so a small network can grow into a big one? And so a hierarchical design is the best solution to that. And so having the network broken into layers and having specific tasks for each layer, then basically simplifies network design, and it makes for easier deployment, management, and network growth. A hierarchical LAN design includes 3 layers as shown in the figure. So there's the access layer, hence where the hosts or users access it. There's a distribution layer, which looks after the routing, pointing the data in the right direction, and the core layer is all about moving data quickly around the network. So if you had a smaller network, you would probably collapse the core layer into the distribution layer, but you would still have at least 2 layers for a smaller network. So, designing for scalability, the network designer must develop a strategy to enable the network to be available and scale easily and effectively, using expandable modular equipment or cluster devices that can be easily upgraded to increase capabilities. So you design a hierarchical network to include modules that can be added, upgraded, and modified as needed. And so, of course, you need to have a good hierarchical addressing strategy that matches the hierarchical physical design of your network. And then you need to choose the routers and switches, multi-layer switches, to limit broadcast and filter undesirable traffic from the network. You can implement redundant links between critical devices between the access and core layers, just so there's less single points of failure. And so redundancy, again, is about that. So it prevents or at least minimizes disruption in network services when you have failures of devices or links or whatever it is. So as I said, minimize the possible single link points of failure, and so you have duplicate equipment and provide failover services for critical devices as necessary. Redundant paths offer alternate physical paths for data to traverse a network. Spanning tree would be required so that you can prevent layer 2 loops. STP provides a mechanism for disabling redundant paths on a switch network until the path is necessary, such as when a failure occurs. So it disables a link, and then when a failure occurs, it may actually be needed again, it can re-enable it basically. So a failure domain is much the same as a broadcast domain and a collision domain. The smaller they are, the better, basically. So a well-designed network should limit the size of a failure domain. So in other words, it's the area of the network that is impacted when a critical device or service fails or has problems. And so, how many users are going to be affected if this device fails, and so on, basically. So the function of the devices that fail will determine the impact of the failure domain. So redundant links and reliable enterprise class equipment will minimize disruption. Smaller failure domains reduce the impact of a failure, but also make troubleshooting easier. So if it's a small area affected, it can localize where your problem is. So in hierarchical design model, it is usually easier to control the size of failure domain in the distribution layer. If network errors can be contained to a small area, which will impact fewer users. When using layer 3 devices at the distribution layer, every router functions as a gateway for a limited number of access layer users. And so switch block deployment. So routers and multi-layer switches are usually deployed in pairs with access layer switches evenly divided between them. Each block acts independently of the others, which reduces the impact of the failures. So increasing bandwidth. So of course, in a hierarchical design, as you go higher up the levels, there's going to be busier and busier links. And so some links between access and distribution switches may need to process a great amount of traffic than others do. And so basically, you can combine multiple links together into that are treated as a single link. And so you can, of course, double or more the bandwidth. And then, and you still have the reliability as well. If one of those cables were to fail, the link would continue to work without that cable working, and so you still have single points of failure being lessened, but you can actually utilize all the traffic. And so your ether channel exists between switching ports, or it can be between a switch and a server as well. And so you can basically load balance the traffic over more than one link, and so increase your bandwidth. So, of course, wireless connectivity is getting more and more important as each day goes past. And so, again, access point does belong in the access layer. And so, of course, the advantages of wireless is it gives you increased flexibility, reduced cost, and you can adapt to changing requirements. End devices require wireless NIC, of course, to work, but most devices have that built in, and of course they need to have the appropriate software and drivers. And of course they need to have a wireless access point to connect to. So routing protocols. So again, with a hierarchical design, you can also, with very large networks, you can actually have a hierarchy in your routing protocols. And so the example given here is OSPF. And so OSPF can actually be divided into multiple areas. Area 0 is always the backbone area, and then the other areas connect to it. And so it can sort of reproduce your hierarchical physical design in your routing protocol as well. And so the beauty of being able to do that is it actually lessens the amount of traffic required for OSPF to work, because it sort of localizes things a little more, and also it makes the routing tables more stable between the areas, and so it just makes the network more reliable. And so EIGRP is another routing protocol that's available. That's a Cisco proprietary one, and that does many features like OSPF, but not quite as hierarchical as OSPF. It doesn't have multi-areas. Okay, so selecting devices. So basically, you need to choose the correct hardware for the job it needs to do. And so for network enterprises, you've got a campus, LAN switches, cloud, data center, service provider, and virtual networking. And of course, switches come in in different configurations. And so you've got fixed versus modular. So fixed means that's it, you can't change it. Modular means it's actually got slots that you can actually add extra bits of hardware to increase its abilities. Stackable versus non-stackable. So stackable basically means that you can actually join the backplanes together of multiple switches and they behave as one. And then of course there's the size of the switch, and so normally measured in rack units. So how high is it basically? And then of course you've got to pay for it. So there's a cost, there's port density, there's power required, and what reliability do you require? And so the port density of a switch refers to the number of ports on a single switch. Fixed configuration switches support a variety of port densities, so 24 port, 48 port, and so basically, and of course then they will have uplink ports as well. Then of course they're your fixed ones, and then of course your modular switches, looking at that 6500 on the other page there's so many slots there that you can port in devices, and so you can have possibly thousands of ports. And of course you can actually put in other modules that will be a layer 3 module or whatever it might be. So the forwarding rate basically is how quickly can a switch forward packets, and so a 24 port switch would need half the forwarding rate of a 48 port switch because it's got half as many hosts. And so basically access layer switches typically do not need to operate at full wire speed because they're physically limited by their uplinks to the distribution layer, but higher performing switches, higher in the layers, do need to be able to move more data. Power over Ethernet is another thing you can consider. So basically you can power some of the smaller devices through the Ethernet cable. So typically it's IP phones or wireless access points, and so it basically just decreases the cost of deploying those devices by not having to have an electrician put in a power point as well as a data point, and so it can make things that little bit cheaper. Multi-layer switching, of course, is where typically switches are layer 2, but you can actually set some or most switches up, enterprise level switches, up to be a layer 3 router as well, and so that can forward packets between VLANs typically in a much faster fashion than a router can. Also saves traversing extra links to get to a router, and so so it is a very efficient way of doing things, and they actually have ASICs, or application-specific integrated circuits, that actually are built into the hardware so that they will actually forward those packets independent of the CPU and basically at wire speed, so much better performance. So when it comes to routers, you have some requirements, and so routing is required within the distribution layer of an enterprise. Without routing, packets cannot leave the local network, and so they're critical devices because they're responsible for connecting businesses and homes to the internet, interconnecting multiple sites within an enterprise, connecting ISPs on the internet, translating between different media types and protocols, and finding alternate paths if a link or path goes down. So they do all these things. And so basically they'll join locations, you can logically group hosts into departments as well as add security between those departments, and of course routers stop broadcasts from traveling further. They also serve other important functions like containing broadcasts. You can basically what I was speaking about. So again, how much budget do you have and what do you need to do is always some of the questions you'll ask when you need to purchase routers. And so you've got branch net routers, so they can optimize branch services in a single platform while delivering an optimal application experience across your branch and WAN infrastructures. Then you've got network edge ones, and so they deliver high performance, highly secure and reliable services to your campus, data center and branch networks. And then service provider routers are, of course, dealing with a hell lot of traffic from within an ISP or someone like that. And so again, much the same as switches, the routers can come as both fixed and modular models. Fixed series ones are pretty much the only ones these days are 800s. Even the 1940s we've got are at least partially modular. Not a whole lot of expansion cards, but there's some. But of course, as you go up the levels, all the way up to those service provider switches, you can actually have ones that have, again, tens of expansion slots so that you can change their behavior. Okay, so talking about iOS, the operating system, and so basically iOS, the previous major version of iOS was version 12, and then they moved to version 15. I understand why they didn't do 13. I'm not sure why they didn't do 14. But anyway, but with it, they also changed the way that the iOS files are organized and also the licensing of the operating system. And so it's always been that if you buy a Cisco device, it comes with the basic operating system, and so that will do most things, and pretty much everything we've done up until now has been supported by the basic operating system. But of course, some extra features that you may want to do will need the extra feature sets. And so previously with version 12, you needed to actually download a different version of the operating system, install it, and then use it. With version 15, it actually all comes in one file, and then you apply the license that actually applies to what feature set you've paid for. And so there's data center, there's security, there's enterprise communications packages, and all kinds of things like that. And so yeah, basically if you want those extra features, you'll have to pay more for a bigger license, basically. So how do we manage these things? And so out of band, you either use the console port, which of course is that light blue color-coded port on the back, on the outside of the router, or there's also the auxiliary port, which I think is normally black, and so of course that's actually designed for a modem to plug into it. And so of course console port, you're going to be in the same room as the router. With the modem, that could be a longer term solution where you actually can dial into a remote office and fault find a router if it's got problems. In-band, of course, is using the network, and so basically you need to know the IP address or the DNS name for the device, and you can connect to it using Telnet or SSH or a web browser or something like that, and then do remote configuration. And so you could be on the other side of the planet, depending on how your devices are set up. And so of course we've got basic commands there, and so this one is showing a router, so it's setting the enable secret password, and then console passwords, VTY passwords, and then setting up IP addresses on interfaces, and that's a very basic setup. And then that last line there is router rip, and so that's actually going to set up a routing protocol. And so of course host name is always a good idea to at least describe somewhat what device you're configuring at the moment. Passwords, of course, are security. IP addresses is so it will work. Of course, routing is so it will be able to route packets to remote networks. Once you've made your configuration, you then need to save it to NVRAM so that if the router reboots, it will maintain the configuration you've applied. And so once you've done it, you would actually then use show commands to see that the end results are what you planned on having. And so show IP protocols shows you information about the routing protocols running on the router. If you do show protocols, that shows you the layer 3 protocols, so IPv4 or IPv6. Show IP route shows the routing table. Show interfaces shows you the status of all the interfaces connected to this device. Show IP interfaces gives you layer 3 information more in depth. If you do brief, it's one line per interface, and then there's CDP, which of course is Cisco Discovery Protocol, and that can be a way that you learn about neighboring devices. Switches, the configuration is mostly the same when it comes to host names and passwords and the like. The major difference is a switch doesn't need an IP address to do its job, or to layer 2 switch at least. The only reason it would need an IP address is so that you can do remote administration on that device. And so that's when you would do it on the switch virtual interface or interface VLAN 1 as it is there. Of course, when it comes to layer 2 stuff, you can actually do switch port security and other such things like that on ports to control these things. Again, once you've got it configured the way you like, you would copy that running config into NVRAM so it's maintained long term. And so some of the show commands will be the same on a switch as a router. Others, because they do a different job, will be different. And so show port security will show you what ports have got port security assigned. And show interfaces, well, there's normally a lot more interfaces on a switch, so that's going to give you a lot of information. And of course, show MAC address table is the equivalent of show IP routing table, because yeah, that's how switches forward frames using a MAC address table. And so we're up to the summary now. And so we've looked at the design of designing a scalable hierarchical network, and we looked at what devices we can use and a very basic rehash of configuring switches and routers. There's the logo. So this will end the video. Have a nice day.